Hi all, welcome back to this channel. What if you can hand AI agent something you want to optimize and give him a way to evaluate that and you sleep? AI agent can run hundreds of experiments on it and you will wake up in the morning with the best solution committed to your Git. This is not hypothetical. Andrej Karpathy has open sourced this and I think many of you know about this. But the main thing we will be talking about in this video is auto research applications beyond ML training. I have read many Reddit threads and many threads on Twitter talking about it, and people often think about it is just limited to model training, but it is way beyond that. And we will be talking about that mainly in this video. We will go through all the auto research. I have added sections in this video so you can skip whenever you like. So we'll be starting with intro, what is auto research, the three file architecture, and then we will go through applications beyond ML. I will also show you a live demo which is not ML training. Then we will look at the bigger picture, and at the end we will wrap up. So let's start. So let me introduce you to Andrej Karpathy if you don't know. He was founder of OpenAI. He literally helped start the company and build ChatGPT. He also led Tesla Autopilot C. He led the neural networks that powered self-driving. He was the senior director of AI there. He created some of the most important open source AI projects. If you know NanoGPT, LLM.C. If you ever have fine-tuned a model or studied transformers, you have probably used his code. He is also a guy who coined the term vibe coding. So previously people don't used to love that term, but now everyone is using it. So he was the guy behind it. So auto research basically started when Karpathy had training script of GPT-2 model. He has been hand optimizing it for months, tweaking hyperparameters, trying different learning rate and other things. And he asked himself, why am I doing it manually? He created this auto research to help him train GPT-2 model, and the results were very good. So let's see in high level view. So agent will start with the hypothesis. I am doing this change and this change might improve the metric. You have to give agent a way to evaluate. The matrix also has to be one. It will look at only one metric and it will modify that file. It will run the evaluation, get that metric. If that metric score is improved, it will commit that, and if it is not improved, it will reset, and again it will start with the next hypothesis, and it will keep doing it as a closed loop, and will run hundreds of experiments. One more thing I want to point out here is every experiment will be of same time, because we cannot compare experiment which was run for 5 minutes and 50 minutes. Obviously the 50 minutes experiment will be better than 5 minutes experiment because it had more time. We cannot compare that. Every experiment should be of similar time, and then the scores will be compared, and if the scores are improved, it will be committed, otherwise it will be reset. So let's move to the three file architecture. This is the file which will be written by you. This will be the program MD file where you will write all the objectives, all the constraints, all the protocols. Let's say what we are optimizing as an objective, you can write. In the constraint you can write what can't agent do, and in the protocol you will write how will the agent behave. So you can think of it like something of a system prompt. You will write this. You will have to write everything here. Also there will be a train.py. This file will be modified by agent. So there will be an initial file, something you want to improve or optimize, which will be in this file. So as you can see by the name, Karpathy was training his GPT-2 model, so his name is train.py. This file will be a mutable file which agent can edit. Code config prompt, you can do anything with it. You don't have to worry about it. And this will be the third file, which will be the prepare.py. This will have the evaluation and metric which you will give to agent, and agent will use this metric to see what the modification it has done is better or not from the previous file. So based on this, he will either commit it or he will reset. One more thing, this file will not be touched by agent, because if he touches this file, then he will obviously be changing it every time to show that the changes it has done are better than previously. So this metric file will not be touched by agent. Make sure that this is only one metric. So let's discuss about the applications beyond ML. So auto research can work anywhere where you can score. So if you have one file one metric and a way to score, then you can run auto research on it. It is a closed loop, it is a time box loop. Every experiment should be of same time. It is the same pattern you can apply to prompt engineering, your API performance, your trading strategy, your SQL optimization, your Docker builds, and your email marketing. You can apply this everywhere. Just you have to be ready with the metrics. So let's say for FER performance, you will check for P99 latency. SQL, you can check for execution time. Docker builds, you can check for the size or build time, and you can apply this to anything. The only three conditions for success are: one, scalar metrics; automation, evaluation. So automation, evaluation, I have not talked, but the evaluation obviously should be automated, because there should not be any human in the loop. As it is auto research, agent should have a way to evaluate the changes it has done and get a score based on it, and you should have only one mutable file. If you have these three things, you can use auto research on it. If any condition of these three are missing, auto research will fail. So in live demo, I want to show you this problem which I will optimize. Let's understand the problem first. It is a standard spiral matrix problem. You might already solve this in LeetCode, so I will be showing you this. So there is a matrix where we have some rows, some column, and we have to return all the elements in spiral order. Let me take you to the code base. This is our WrapUp. I have my program.md file. Here I have written all the objectives, all the behavior, and all the constraints. I have written some other things too. This is the file which I have written for agent, so that it can understand what it has to do. Let's go to my eval.py file. Here I have added test case for my spiral matrix. These are standard test cases, and it will only show one metric: how many test cases are passed from 25 test cases. So either 8 or 10 or 20, based on it, it can improve. So my metric here, the scalar metric, will be how many test cases are passed. And here is my initial solution.py file. I have intentionally made it wrong, so it will only pass few test cases, and my A agent can improve on it based on the scalar metrics. Let me run my python.eval file to show you the initial scalar metric. Only 8 out of 25 test cases are passing with the current code we have. So it is intentionally wrong, but our agent will improve it. You will see. Let's fire up Cloud Code and give it the prompt. This is the prompt I have written. I have told it to read the program file and follow the experiment protocol. It will start by running the baseline eval which we just ran. It will begin improving the solution pre-y. It will not stop, it will not ask any question. It will keep running experiments autonomously until it reaches 25 by 25 test cases. Generally it will take some time. Once it is done, we can see git log and we'll see what it has done. As you can see, it is done with the changes. So let's see what it has done. It ran our initial eval. Solution is just row by row traversal. I will implement the correct clockwise spiral algorithm. So it knows this is the baseline, so it added some code, and then all the test cases passed. So I was not expecting it, but it is obviously Opus 4.6, and this spiral matrix is basically a known problem. And so but you get the gist, right? If you have some complex algorithm, it will keep evaluating and keep solving the problem one by one. If it is getting a perfect score after only just one iteration, it is stopping the loop. So this is a fair one shot, so we will not complain about it. It has committed the file. We can also go to this new terminal and see this command git log -1 line, and it is showing what it has done. So it has run only one experiment and it has one shot at it. You can give it yourself some complex problem to optimize, and it will keep running experiments one after another. So if you have chosen some basic model, then it will not be one-shotting this, but it is Opus 4.6 is the best frontier model. It has one-shotted it, so it's fine. Let's talk about the bigger picture here. Let's zoom out what we just saw. We saw a scalar metric, a file which agent can modify, and evaluation file which agent cannot edit. Agent can run a lot of experiments on it, and the best score committed to your git. So you can use to optimize LeetCode problems, optimize prompts, optimize Docker files, optimize trading. You can literally optimize anything. The pattern will not change. Edit one file, score it, commit or revert and repeat, and you will provide the metric and agent will provide its idea. So the research is auto, but it cannot cheat. So let's talk about Karpathy's end vision here. There was a experiment called Sati at the Red Home, where we can donate our spare computing power in search of alien life. What Karpathy wants to build is something similar, but in terms of AI. Basically, he wants millions of AI agents working on optimizing different problems, running research loops on different problems, and we can allocate where all this research will go. He's also predicting that frontier AI labs we have, like Anthropic and Google XAI, will have some form of auto research, because if you see, it is way faster than how humans will research. AI labs are spending millions of rupees on researcher doing research manually. Karpathy has made this loop open source and distributable, so anyone can use it. I will be also be linking his GitHub repo in the link, so you can go and check it out. It is very good. Also, let's talk about what we are automating: execution. The judgment here, it is not automated. So what agent handles is it can write the code changes, can run the experiments, it can compare the results, it can commit or revert. What we provide is choosing what to measure. We can set the right constraints, we can tell it what is the right file it has to edit, and we can tell it when to stop. If you set the wrong metric, it will confidently optimize the wrong thing. So a person who sets up the loop correct will outproduce a team doing it manually. This is the wrap up on auto research. Let me quickly summarize the auto research. If someone is directly coming here, can check this image and you can quickly recap whatever we have learned from it. Obviously, it is a closed loop which agent runs based on our rules given in the program.md file, and it can evaluate using this file, and it can change this file. If it is better, it will commit, otherwise it will revert. It will only work when we have one clear scalar metric. Evaluation is automated, and one file will capture whatever it can edit. The takeaway: if you can score it, you can auto research it. So if you have a way to score it automatically, you can auto research it. This is the Karpathy's auto research repo. I will be adding it to the description of the video, so you can quickly check it out. So if you like this video, press that like button, click on the subscribe button too if you want to check the new videos which I will be posting soon. Also click on the bell icon, you will be notified when I post a new video. And happy coding. See you in the next video.